네, 한성민 씨 안녕하세요. 네, 정상목 씨 안녕하세요. 네, 아직 박건우 씨가 안 오신 것 같네요. 네, 박건우 씨 안녕하세요. 자, 그러면 시작을 하도록 하겠습니다. First of all, sorry for a few minutes delay in lecture 9 start. Okay, so I had a family issue. So anyway, sorry for this a little delayed start of lecture 9. And why don't we just directly or immediately start the lecture 9? Do you have any question? Any question on the previous lecture? So previous lecture we had considered very simple system where we have just 3 points inside. So since we have applied actually just directly boundary conditions for these two top and bottom point, and effectively we have only 2 points. So in a vertex side we have only one vertex, so vertex number 2, and that can contribute, for example, if we just take our usual or previous discretization scheme, then we will have just phi sub 2. So this is the electrostatic potential assigned to vertex node 2. However, if we expand our previous discussion on region-based assignment of unknown variables, then we immediately find that instead of this phi sub 2, we can define something like this: phi sub 2 defined on, for example, region 1 and region 2. Of course, in many cases, the physical quantity will be the same between these 2 points. However, we can see, okay, so that was our previous lecture. So if you have any question, then please interrupt me. However, although for electrostatic potential, we can assume there is a continuity of the electrostatic potential, but of course we can find many other quantities which does not show the continuity. For example, how about the conduction band minimum? Conduction band minimum for R1 and R2. You know that if this upper region is oxide and this lower region is silicon, and we know that there is a significant difference between the conduction band minimum of silicon and conduction band minimum of an oxide region. So simply speaking, although we are talking about the same position, only with different regions. However, since this one is corresponding to an oxide region and this one is corresponding to a silicon region, so we can say that even though they are belonging to the same position, we have to have such kind of relation. So EC R1 and 2, the oxide one is actually 3.1 electron volt higher than the silicon conduction band minimum. So maybe you have seen it before during your other courses in your undergraduate level study. So maybe you remember that something like this. For example, don't forget about the difference in this slope and slope. Yes. Anyway, point is now you have difference here. And this one is 3.1 electron volt, and this value is somewhat high value. So the barrier, we have a very high barrier, so it is difficult for our electron penetrate into this oxide region. So you remember this ones. So when I come back to our main discussion, so there is no guarantee that every quantity, every physical quantity is continuous across the interface. So in the case of electrostatic potential, it is just one fortunate case, one lucky case, we have the continuity. So more precisely, if you have read our book, the introduction to the computational microelectronics, you can immediately understand the reason why we have the continuity of the electrostatic potential. Static potential is obtained by our way for defining this electrostatic potential. So if you have not read that part, then I wanted to recommend you read our book. Okay, so where can I find it? So please wait for me. Okay, great. I got it. Okay, why don't you just visit our section chapter 2 and section 8. So section 2.8, please read this part. So I think that most of you have already seen it before. However, please have a look at it once again. I mean that when we determine the value of electrostatic potential, actually we have a certain, certain degree of freedom to add up to a constant. However, when we in this TCAD simulation, the device simulation, we intentionally define the electrostatic potential as the quantity referring to the intrinsic level of that material. That is not the case. By using our electrostatic potential, when you multiply minus Q, then this one usually refer the intrinsic level of our reference material. So usually reference material is a semiconducting material, in our case silicon. So although, for example, in this part, since R1 is an oxide region, so actually if we define the electrostatic potential as a quantity referring the intrinsic energy level at that point, then maybe we will have the discontinuity. However, instead of that, although we are talking about oxide region, but this electrostatic potential refer the intrinsic energy level of silicon. So that's the reason why we can have continuity. So I wanted to ask you many things, but please check that you have read the section 2.8 and you understand the meaning of electrostatic potential. So that is the reference material. And now finally you understand the continuity of the electrostatic potential is a special consequence of our special setting, like all of our electrostatic potential is reassigned to the reference material. Okay. Oh, sorry about that. Okay, I think that something is wrong with my my sketchbook application, so I just wanted to restart it. Okay, then I can write and erase. Okay, so I think that this is understood. These factors are understood, and if you cannot understand my explanation about the continuity of the electrostatic potential, then please let me know, because this is a really fundamental thing we have to understand before our discussion today. So if you don't, please let me know. Then let's come back to our system once again. So now we have here 3 points, and let's say that this one is called V2. Then in this case we can define phi2, vertex 2 and R1, and also you can define phi2 and region 2. Then when you consider the source-free Poisson equation, let's just think about this simple form, like round dx and epsilon. Epsilon can be a function of x and d phi over dx. This is the form of our source-free Poisson equation, and an usual way to proceed is just to integrate our equation from what? So from integrate it from x sub 1 plus 5, the midpoint between b1 and b2, and integrate it up to the upper limit becomes 2.5. So the midpoint between vertex 2 and vertex 3. And here we have the total derivative of something, and that is just 0 because the right hand side is just 0, even though when you perform the integration it becomes obviously 0. So now let's go to the next part. Then we can find that we must evaluate the phi epsilon d phi over dx evaluated at x 2.5 minus, yes, I'm just repeating the contents of our previous lecture. However, you can find that that's simple. So when you evaluate it, and now we have to introduce discretization. So now discretization looks like this. When we apply this epsilon to our point 2.5, certainly it is silicon. So we can say silicon and delta x phi 3 minus phi 2, but R2 appears here. So anyway, R2 appears here, and minus epsilon, now in this case oxide, and the difference is once again phi 2 minus phi 1 divided by delta x equal to 0. Of course, here I made an assumption that the points or vertices are spaced with equal distance. However, if you wanted to be more general, then of course you can use this one, and of course you can use x2 minus x1. It's not that difficult to extend it. Yes, and we know that this is really works, and we have already solved it for simple one-dimensional structure because all of you have done some exercise on the contents in chapter 2 of our introduction to computational microelectronics. So computational electronics, so you can now do it. Yes, but point is this one. Here we have phi 2, and here we have phi 2. Previously we just assumed that there exists only one phi 2 because the continuity of electrostatic potential was assumed. However, now we cannot write in this way. We have to ask ourselves, for example, yes, here we have 2 phi 2. Then what is it? And what is it? Because we can find both of phi 2 and R1 and phi 2 at R2. Also phi 2 R1 and phi 2 R2. So what is the required quantities for these two terms? The answer is really straightforward. For example, if we consider this first term is evaluated in our region 2, and you know that this second term is evaluated in our region 1. Yes, region 1 is the upper region, and that is oxide region in our assumption. So simply speaking, what we have to understand is, yes, now we have to write it down in this way. Here we have to have phi 2, but at R2, and we have to introduce phi 2 at R1. So that is required. Of course, since phi 2 at R2 or R1 are identical, so actually this equation can be reduced to our ordinary or previous expression. So simply speaking, I'm just saying that first we can have this expression. However, since we have two different variables, phi 2 at R1, R2, so this is not sufficient. Yes, because we have introduced two phi 2 values, so we have to introduce one additional equation. Of course, the additional equation is so obvious, simply speaking, so that of phi 2, that of, okay, so potential at of potential for region 2 and potential for region 1 should be the same. So simply speaking, the problem I asked you in the previous lecture can be answered in this way. If we introduce two different potential values at interface node, then by providing the continuity of that quantity, our system can be once again determined, and you can solve that problem. Okay, so maybe you remember that we have discussed about really how can I say, simple expression. So do you remember? So if we make a simplified version of our expression, then you will find this one, 0, 0, 1, phi 1, phi 2, phi 3. If we do not allow the region-wise assignment, then we will have only one single phi 2. Then here we have directly boundary condition, and also we have a directly boundary condition. And if we just normalized everything, so just to say all quantities like epsilon or x2 minus x1 or x3 minus x2, if they are normalized, then we can write down in this way. So this is the form. So what is here? One is the one shown here is simply the one related with, epsilon oxide divided by x2 minus x1. And what is value 1 here? That is related with epsilon silicon divided by x3 minus x2. So you can easily understand those numbers. So although this is just written as 1, yes, anyway, we just wanted to check the pattern. So if we have this kind of system, then the answer becomes really clear. Yes, phi 1, phi 2, phi 3. Of course, we do not use the matrix solver for this simple case. Yes, please read the third law. Yes, phi 3 becomes, just 1. Okay, so from the third row, we can immediately find that phi 3 equal to 1. And from the first row, we can also find that phi1 equal to 0. So now, since phi1 and phi3 are given, then let's try to evaluate it our second row. Then yes, so phi1 does not contribute, then we will have 2 minus 2 times phi2 plus 1 times phi 3, it becomes 1 equal to 0. So from this one, we can immediately find that phi 2 equal to a half. So now we find this form. Yes, with this normalized pattern, then or normalized coefficient, we can find this rule. And this just represents that the solution for the second point, the vertex number 2, can be obtained by interplay of the boundary conditions and correct equation at vertex 2. But that is not our main purpose. What is our main purpose? So our main purpose is to make an analogy with, instead of this 3-point discretization, so we want to make some analog relation for our 4-point or 4 unknown variable discretization. So now we have ES. Here we have 4 different variables, and we have a 4 by 4, and yes, also we must have this one, the right hand side. And once again, if we apply the directly boundary condition for top and bottom context, then we will have 1, 0, 0, 0. You know it, so that becomes just 0, and it is not that difficult. Also, when we apply the boundary condition for our phi 3, then we will have 0, 0, 0, 1, and that will be just number 1. Then point is, how can we assign our two equations? For example, we have to have R2 equal to R1. Okay, sorry about that. Yes, we have to now insert these two equations. So, maybe you feel that it is not that difficult. For example, let's do it. For example, 1 minus 2, 0, 1. Can you see it clearly? This second row shown here is actually corresponding to the second row of our previous 3 unknown variable case. So 1 minus 2, 1. So the unknown variables related is phi 1, phi 2, and phi 3. And in this case, now we have phi 1 and phi 2 at region 1, and phi 3 are involved. Yes, and also we can define something like this: 1 minus 1. How about this? So this third row just says that minus phi 2 at region 1 plus phi 2 at region 2, the sum of them is 0. So simply speaking, this continuity is implemented at the third row of our implementation. So then maybe you can feel, oh, this is too trivial. So we have spent plenty of time. However, what we have done is just say that select one node and evaluate it, and for other node, non-selected node like this, we just impose the continuity. So anyway, let's go to the solution of this equation. Then how can we have the answer of this simplified or normalized system? So let me just do it here. And now we have phi 1, phi 2 R1, phi 2 R2, and phi 3. Then now it becomes, yes, once again. Then also from the boundary condition, it becomes 0 and 1. And if we just solve or consider the second equation, then since this number, so this is none and this is none, so we can again find that this becomes just 0.5. And finally, when we visit our third row, it says that we have a continuity of the electrostatic potential at the interface node. So we will have 0.5. So of course, you may feel that this is really redundant treatment for our simple case, but please note that in general cases, we have many examples where we have to introduce this region-wise unknown variable assignment. So now you know the necessity of this treatment, and you can find this expression. Okay, so I think that this is actually the contents we have covered in the previous lecture. So previously, in the previous lecture, instead of having this form, what we had was like this. At that time, we had a long discretization like 1, minus 1, 0, and 0, 0, minus 1, 1. Obviously, this second row and third row just to discretize the vanishing gradient of the electrostatic potential at each edge node. And you know that, so since we don't have any connection between region 1 and region 2, in other words, let me just highlight them. If we have this type of discretization, then actually we can find that our Jacobian is just separated into two parts, and there is no non-zero component and no non-zero component. Simply speaking, R1, the region 1, and R2, the region 2, are completely separated and they do not communicate to each other. However, let's just come back our improved or correct implementation, then maybe you can easily find that this one. Now we have minus 2 and 1 and 1 minus 1. So simply speaking, we have the off diagonal blocks which does not vanish. So this region 1 and region 2, it has its own small Jacobian matrix or small system matrix. However, also they are communicating with this off diagonal one, so circle green circled ones. So since it does not have it does have non-zero entries inside it, so they are communicating the information. Okay, so do you have any question up to now? Okay. You're right. So, Mr. Chong, you are right. I made silly mistakes. So, you are quite right. I have to write down in this way, -1. Yes. Thank you. Thank you for pointing out my mistakes. And please go ahead, Mr. Park. Okay, thank you for really nice question. So your question is really well assigned my lecture progress. Actually, from now on, we'll talk about exactly that topic. So yes, you are quite right. So right now, let me just repeat your question. Right now, we just arbitrarily select the phi 2 for R1 region as the more meaningful one, and we just impose our boundary condition or source-free Poisson equation for phi 2 R1. However, as he, Mr. Ba, correctly pointed out, we can think about one alternative way. Instead of having selected this one as the reference one, why don't you have, for example, -20? Do we have any difference? So you can easily understand there will be no difference at all. So simply speaking, selecting which one, R2 for phi 2 for R1 or phi 2 for R2 doesn't make any difference. However, it's a little bit annoying that we can allow arbitrariness to our implementation. So then, is there any rule for selecting which one is preferred for the implementation and which one is less prepared, and just to give the continuity condition? Which one should take the real equation, the source-free Poisson equation, and which one should take the continuity boundary condition for interface node? That is your you means that Mr. Park's question, and that was really good. So I wanted to say that in principle, no, how can I say, no preference is provided. However, in reality, in reality means that in our real application, so, sorry about that. So mm, in real application or real implementation, we have well-defined rule for selecting so-called representative node. So Now once again, let's think about these 2 points. Phi 2 R1 and phi 2 R2. Which one is more representative? So please note that this R1 is oxide and this one is silicon. Okay, for source-free Poisson equation, they are treated in equal base. However, think about, for example, electron continuity or hole continuity. Then what will happen? For electron continuity and hole continuity, actually this node point, for example, N2R1 or P2R1, they are not defined at all. There is nothing like this because the oxide region does not have the electron density and hole density, since the oxide is regarded as a perfect insulator. However, if we consider this one, then we will have N2R2 and P2R2. They have really a good physical meaning, and we really wanted to solve and get those numbers. So, are you with me? So, simply speaking, you may feel that which node, so vertex node 2 for R1 and vertex node 2 R2, which one has more physical meanings and which one is more important? So without hesitating, all of you can answer that, this one is much more important. Yes. So now we say that in many cases we have the rule like this. If we have the interface between silicon or semiconductor and oxide or insulator, then the priority should be given to the semiconductor. So if we have to highlight the meaningful quantities in our implementation, then we have to select this guy. Of course, this is a boundary, and this guy. Okay, since they are the only node for each vertex, it's okay. And when it comes to the interface node, then we have to say that this guy, the vertex, but point 4, our semiconductor region, should be regarded as the reference point. So simply speaking, the answer should be like this. We must develop a code like 1 minus 2 1 0, because this one has the priority and the remaining one. So the other node should take something like this, just having the continuity between the interface nodes. Okay, so I think that Mr. Park's question was really important, and now we understand that should be the correct implementation. So once again, although I have wrote in this way, 1, 1, minus 2, but actually that is related with some quantities like epsilon silicon divided by 1 over x3 minus x2. And although I write down here, but it should be regarded as so x2 minus x1. I'm just showing you the pattern, so that's the reason why I made it just number 1. But please note that in your real implementation, you have to consider this kind of real coefficient. And of course, this minus 2 will be the sum of these two numbers and taking the negative sign. Okay, then if you listen up to now, then you will feel in this way. Oh, then compared with our previous scheme for three unknown variables, this one does not make much difference. Yes, if we just consider the small system generated by this one, then we will have the identically the same system. So that's not that interesting, and that is too trivial. But my point is like this. Okay, but anyway, before starting our more implementation related discussion, so I wanted to ask you, all of you are with me and understand this correct implementation, correct Jacobian matrix or system matrix we have to have. Okay, if you can understand this form, the right form is the true or correct or desirable, then how can you make it? That is the remaining task. Oh, then how can you evaluate it? Think about this one. Now, instead of this highly trivial structure, now think about a little more generalized form, like this. Now, you have certain points. Wow. Then, even in this case, now let's assume that you must solve the source-free Poisson equation. Then how can you proceed? That is my point. Okay, once again, let's call it as R1, and this is the oxide region. And let's call it as R2, and this is silicon region. Now you understand, for certain vertex V, let's say that this one has the index V, then we can define phi index V and R1, and also we can define these two different quantities. Yes, wow. And you understand, between them, this guy should have the preference. So yes, so now we have to say that this one does not have the preference. Then how can we implement this one? Of course, the desired one is like this. One. So since we have took it as the reference one or representative one, then we will have this form, and quite similarly we have to impose these two conditions, like phi for R1 minus phi R2 equal to 0. And we can also consider the second equation, the source-free Poisson equation. Source-free Poisson equation, where this the quantity at R2 occurs only here in this part. We don't have any quantities like phi sub v at R1. Nothing like this. That is our approach. Then I think that most of you can understand this one quite well. But point is, think about this construction of the source-free Poisson equation. So please concentrate from now on. Yes. Now let's say that you have this kind of discretized node. Great. So now your system will just look like this. Yes. Yes. Beautiful. And now I'm asking you, please try to implement your source-free Poisson equation. So what should you do? Okay, then you have to learn over your elements. So here you can find one element, and here you have one element, and here you can have also one element, another element, and also you can find another element. Yes, you can learn them, but point is, when you learning over elements, for example, let's say that you are currently working on this element, then what will happen? You will just consider this a triangle, and yes, you can find nodes. Of course, you can easily understand this is just a magnified version of this triangle and this triangle. So now you know it. So then what is the material or what is the region of this triangle element? And the answer will be just R1. So every quantity, every physical quantity is related to what? Related to R1. So my question is now here, when you evaluate it, you don't have my comment actually, you don't have something like this, R2. It is not available to you in a local sense. So of course, if we are looking at from the global point of view, of course, this phi for interface node and region 2 is always available. However, if you are just localized and concentrate on this small triangle, then you don't have the quantity like this, nothing like that, and the only one you have for this vertex is just R1 quantity, not R2 quantity. That's the problem. So let me just come back to our simplest case once again. Now, this is really related with the implementation. So we have 3 vertices. Okay. Now you understand. You have to implement the source-free Poisson equation for this node. And now you understand what you have to do is actually calculate the difference between flux. So flux means that epsilon silicon d phi over dx, at this point, and epsilon oxide d phi over dx at this point. And if you calculated this one, in order to make everything localized, then you just consider one single edge first, and you move to the next edge next. So when you consider this first edge, the information available to you is only phi 1 and phi 2 and r1. Once again, of course, this quantity is equal to r2. However, this relation should be supplied by our additional equation. We cannot use this continuity from our construction. So, are you with me? It is because this continuity, the continuity of electrostatic potential or continuity of a certain physical quantity is not guaranteed. Actually, in some cases, we have to generalize, we have to have a general relation between certain interface quantities. So, unfortunately, if we discretize it in this way, for example, oxide x2 minus x1 and phi 2 r2 minus phi 1, then obviously this one is contributing to this minus 2 here. However, unfortunately, we don't have this quantity. What we can have is, instead of this, now we can only have R1. So the point is, now when we just construct our system matrix in a localized fashion, then what we can get from collecting our information is not this minus 2, but anyhow we have to have here minus 1, because this guy up here, because when we construct or when we consider the edge connecting the first node and second node, and of course if we move to the second edge shown here, then it will give us something like this, x3 minus x2, and here we have phi 3 minus phi 2 r2. In this case, we don't have no idea about phi, we have no idea about phi 2 for region 1, only region 2 is available. So therefore, even this is not easy. Say that, okay, if phi 2 for region 2 is not available, then okay, I will switch to this way. No, it's not possible, because the construction of a Jacobian matrix is done really in a localized way. So you have to have 1 and unfortunately minus 1 here. Then, well, you feel a little bit uncomfortable, but you find that even with this separation into two pieces, but your scheme once again really perfectly works. You have still correct answer. So that is really well verified by actually solving your system. So let's do it together. So the solution vector will be like this. So solution vector will be Yes. From the boundary condition, we will have 0 and 1, and if we just implement or consider the 0 and 1, then now we have 1 minus 1, this central part, and minus 1 and minus 1, and phi 2 r1 phi 2 r2 equal to 0 minus 1. So it means that we will have once again half and half by solving this small system 2 by 2 matrix. You can immediately understand that it becomes just 0.5 for both values. So simply speaking, you don't have to worry about this separation of unknown variables. Now you can say, oh, this works. This Jacobian matrix or system matrix is originated from localized, highly localized construction of system matrix. So how can you do that in reality? So let's just do it together with me. Okay, now you are learning over your elements, and for each element you just consider your, how can I say, your edges. Then for example, let's consider this guy, this example once again. Here, now consider this point. Then consider if we consider R1, if we consider triangles belonging to the R1 region, then just assign your evaluation result on this row. And please learn over the triangles belonging to the R2. Then of course you will have a certain relation, and they are separated. So let me just repeat it again for our simple equation. Then for the first edge, just learn this simple example. Then you will find that 1 minus 1, 0, 0. That will be the evaluation result for your first edge. And if you are learning over the second edge, then you will have again minus 1, 1. Oh, sorry, minus 1 and 1. That will be your system just after considering the localized construction. And you feel that this is obviously wrong. How? Why we are obviously wrong? Because this flux actually should be merged into this third row. Then how can we proceed? What I wanted to suggest to you is, once after building these two rows, then the next thing is just to merge them. Merge them means that just to make a sum of these two lines. Then what will happen? If we and assign that sum into our representative node, then obviously the answer will be like this. 1, oh sorry, so we just use the same color. 1 minus 1 and 0. That will be the sum of two fluxes. And of course, since this flow is cleared, every information is just dumped into our silicon node, and we have one missing relation. Then of course here we can impose the boundary condition. So boundary condition simply means that 1 minus 1 0 0 0. That is my final answer. So why we are talking about this kind of a quite complicated structure. So think about this more general case. Then how can you solve the source-free Poisson equation in a localized way, not showing the global variables, and just learning over local elements? The way is always consider just a given triangle. Yes, then from that triangle you can find certain related edges, and for those edges just to calculate its contour surface or surface between two vertex nodes, and evaluated this length and this length, and calculated the first order derivative. And when you evaluate it, just to consider your own variable. Your own variable means that the variable assigned to your triangle. Yes, then if you follow in this way, you don't have to worry about, oh, am I connected to the other one, or am I an interface node? So such kind of complicated consideration can be avoided and postponed, and just to collect all of this localized construction. After this localized construction, maybe you will have a long Jacobian matrix, long Jacobian, or in this case a system matrix, but anyway, you will have a long Jacobian matrix because boundary condition is not, interface boundary condition is not properly assigned. After that, learning over the interface node, if you have a certain interface node, then select which one is the representative one and which one is not, which one is the non-representative one. Then just send or merge the information and just assign the summed equation for your reference node. And of course we will have a missing information, and that missing information is supplemented by your boundary condition at the interface node. That is the end of my long story, starting from our previous lecture or even further. So why we are talking about this such kind of a complicated discussion, it is only because if you are trying to implement a two-dimensional implementation beyond just a unified assignment. For example, I don't care about the interface, I will just consider only one variable. Yes, you can do it. So however, this is not the state of the art, or that is the most reasonable way to do that. So the more frequently used method is just to assign two variables for two regions and say that which one is the reference one or representative one, and for representative one just to assign your equation, and for non-representative one assign the continuity of your quantity. Of course, this equation can be easily generalized, so you can add more and more. For example, let's just say that, let me just conclude my lecture with something like this. EC for R1, EC number 2, R2. If we have such kind of unknown variable, then our equation is no longer look like this. So in this case, so oxide one and silicon one, of course they are proportional. However, we will have also non-vanishing right hand side term. Simply it means that the one for oxide is 3.1 electron volt higher than the silicon one. That will be the implication for this physical quantity called the conduction band minimum. Of course, this is not frequently used in our actual device simulation, but in general, we should be able to consider this region-wise different physical quantities. Okay, the time is up, and I have spent quite a long time about how can we treat the interface node. So now you can assign or you can detect which one is the interface node, and since you know that information, the homework number 9 for today's lecture is just to repeat the source-free Poisson equation solver once again with this more advanced way. Okay, so are you all with me? So please repeat that you have understood the homework number 9, and of course due is the next Tuesday morning. Okay, so could you please repeat that you have all understood this one? Then I will wrap up today's session. Okay, any further question? So, if you have further questions, then please contact me through email or our Slack direct message. Okay, then see you next Tuesday. But homework number 9 is quite important for general implementation, so please concentrate on homework number 9. Okay, see you. Bye.